Welcome back. In today's video, we want to show that the instantaneous time function corresponding to the phasor function or the phasor component or counterpart of that function is given by the function of time, v of t, which is a voltage signal. So this is a bit confusing because a instantaneous time function is the same as are in the same form as the function we have here. So this could be an instantaneous time function. If we plug in some value for t, we'll get the instantaneous voltage at that time. So basically what we're trying to do is prove that this function corresponds or is given by the function v of t. So we can do that by first converting our phasor voltage function or our phasor counterpart of this function. It might not turn out to be this, but if it is, this will be the phasor counterpart of our time function. So we can then go ahead and use Euler's identity for both expression on the right. So Euler's identity, we can write that over here, e to the j theta is equal to cosine theta plus j sine theta. So this is then equal to 4 times cosine 60 plus a j4 sine 60 plus 6 cosine negative 60. Cosine function is even, so that will turn out to be a 6 cosine of 60 and a minus j 6 sine of 60. So we go ahead and we cancel, or in this case add, because we can add these two because the cosine function is even with negative 60. On negative 60, we'll get a positive 6 times cosine of 60. So 6 plus 4 is 10. So we end up with 10 cosine of 60 degrees minus a sine minus j2 sine of 60 degrees. So 4 from 6, leave 2. So we then go ahead and evaluate that. We end up with 5, a real part of 5, and an imaginary part of 1.73. We then use our trig identity, not our trig identity, but our complex number properties or relationship between rectangle and polar. So the magnitude, and in this case we're using x as our complex number, the magnitude of x is equal to the positive square root of x squared plus y squared. Angle phi is equal to inverse tangent y over x and we can go ahead and write that our magnitude is then equal to 5.29, and we have an angle of minus 19.1. So this is the phasor component in polar form. We can then convert that by using, or not say by using, but by using. So that is the relationship between the time domain and the complex counterpart of the function in the time domain is if we have a signal x of t, that is equal to a amplitude of a times cosine, a positive cosine, omega t plus phi. We can transform that, or transform that to the phasor domain, and in the phasor domain, the phasor counterpart of the signal x of t is going to equal to the magnitude of that signal in the time domain times the complex exponential e to the j phi. So here we see we have the following expression in the phasor domain. So we can then convert that back to the time, and we end up with a amplitude of 5.29 times cosine. And now we don't have any angular frequency, so we just place our omega t, and we have a negative angle of 19.1 degrees, and x of t is then v of t, because that was in volts. So here we have our expression equaling the given expression. So basically that shows us that the instantaneous time function corresponds to the phasor counterpart of that function. So we did derive the time domain function from the phasor domain. So that's it for today's problem. See you in the next one. Bye.